Okay, so now I would like to talk about something more with BPF, and I call it BPFize your kernel subsystem, meaning use BPF in your subsystem which didn't have BPF before. And I will share some of my experience. So about me, who I am, my name is Song Liu. I'm a software engineer at Meta. For the past 7 years, I've been working with BPF on various different things. And for my daytime job, part of it, I support the BPF LSM use cases at Meta. And most of the material here comes from this experience. So start simple, what is BPF? Well, I don't think I need to read this thing here because I think it's fairly safe. Everyone in the room have more or less heard of BPF. But how about this? How would you describe BPF for someone who has never heard of it? I don't think I have an easy answer. I don't think there is an easy answer. This reminded me of a very well-known proverb in China. It says, there are 1,000 hamlets in 1,000 people's eyes. Yes, according to my research, this proverb comes from China. And this is literally Hamlet by Shakespeare. I am surprised by that. I hope you are as well. So my version of this proverb is there are 1,000 BPFs on 1,000 kernel hackers' keyboard, because different people use BPF for very different things, like schedulers, like TCP, XDP, tracing. So as one of those 1,000 kernel hackers, I would like to share what is BPF in my eyes and how do I use BPF on my keyboard. So here's the agenda today. So what is BPF? This is the official definition from the eBPF Foundation webpage. eBPF is a revolutionary technology with origins in the Linux kernel that can run sandbox programs in a privileged context, such as the operating system kernel. This is very accurate, but it doesn't help the beginner much. Just think about I'm talking about something. It's a tasty food from France that goes well with pesto sauce, and it's often served in its own shell. So if you never tried this, sorry, I cannot remember the French pronunciation, you probably never know what I'm talking about. It's just like BPF. You have never used the BPF. This definition gives you little information. Luckily, we have the second sentence here. It's used to safely and efficiently extend the capability of the kernel without requiring to change the kernel source code or load the kernel modules. Now we have more information to me. And here are some very important ones to me. First, BPF can extend the kernel and it brings programmability. Before BPF, we only can fine-tune the kernel behavior through a few knobs, like sysfs entries, like syscalls, sysctls. But BPF goes all the way to the other end. It brings the full instruction side to do that. And you can do that use that to do many different things. On the other end, BPF is also very safe. No, BPF is also safe. This is a safe guarantee. BPF will not crash the system. BPF programs are guaranteed to terminate. BPF will not read uninitialized memory, so you will not leak kernel secret by accident. BPF will not leak memory, and BPF will not leak reference to kernel objects. And the list is growing. A few years ago, the last one, BPF will not leak reference, didn't exist. But how is BPF safe? The answer is clear, the verifier. The verifier checks the BPF program before it's running to make sure it's safe. And the verifier works with BPF instructions. And that's one of the reasons the BPF instruction is so important. Imagine you want to verify a kernel module loaded in native instructions. That will be a much more difficult task. And then how about performance? Well, a different instruction set doesn't work as good as the native instruction set. So BPF does JIT. Another thing interesting is like it's a sandboxed task program in a privileged context. So it's not a sandbox. You can move it anywhere and still expect it to work the same, right? And this sandbox runs only in the designed privileged context, and in most cases is the Linux kernel. And to fully leverage the power of the privileged context, the BPF needs to interact with the rest of the kernel with some well-defined reusable building blocks, like the BPF map, BPF helpers, and BPF kfuncs. And of course, the use of all these building blocks are verified by the verifier to make sure they will not break all the safety promise. So we have talked about good things about the BPF, and of course, all those things are not free. There also comes with challenges. First, the verifier, to write a BPF program that passes a verifier is quite some task. We have internal user feedback sessions from time to time. People always say, hey, the BPF verifier hates me. And second, we talk about these very useful building blocks. While they are useful, it's not easy to create a new one. This is because we usually want to create some building blocks that can serve multiple different cases, not just for a single use case. That turns out to be more difficult in most time. Okay, now, BPFize your kernel subsystem. I would think it as a pie. So there are 4 top things I need to think about. First, the use case. What's the use case? Why do we need BPF? Then the hook point. Where do you want to trigger your BPF program? Then do you need building blocks to make sure your BPF program works well with the system? And finally, you need to work with the community to get the support. Let's dive in. First, you need to know your use case. Why do you need BPF? Do you need the programmability, or do you need extreme speed of the BPF because it runs in the privileged context? And also, you need to know what are the alternatives and why BPF provide value to the alternative. Later, we'll show more example on this. And also, you need to know how BPF fits in the whole solution. Sometimes BPF is just part of the solution. You need other things. How do you glue everything together? Then you need to design your hook point. In the past, if you look at some older kernel code, you'll see a pointer to a BPF program and some logic try to trigger that. And nowadays, that's really not going to scale. So for most of the new use cases, we recommend struct ops, as I think I've mentioned this a couple times in this conference. I'll give another example later. Also, try to reuse some existing mechanism, and sometimes we see very good solution in very creative ways. Now the building blocks. The old way to add helpers is the BPF helper, but we are not doing that anymore because that is UAPI and that permanent support promise we cannot hold forever. And instead, we use BPF kfuncs. I think it's a BPF helper, but it's not guaranteed to last forever. And sometimes we need new map types. So Here I want to say, try to reuse existing building blocks, especially when you are exploring something new. For example, you can use a hash map or array instead of create a very well-designed map for your use case. Later, we can optimize that, but if you use something already there, going to make your effort to do something new much more smooth. Finally, and also very important, you need to work with the community. If you reach out to the BPF maintainers, they will want to know what's your use case. Why do you want to use BPF? And also be prepared to redesign your solution. It's very often someone proposes something A and end up doing something B and solve the same problem, and often in a better way. And very important, write good self-tests for your any kernel changes. There's a BPF CI runs that for all the upcoming patches. If you want anything there, the self-test is a way to make sure your use case is not broken. Finally, you need to support your code in the upstream kernel together with the BPF maintainers. Now let's dive in a use case, BPF LSM. So what do we need LS for is one of the access control in the system. In the system, we have two types of access control, the discretionary access control, which basically give a permission to the owner. For example, this makefile is owned by me, and I have control who can read, write, or do things with my file. The other end is mandatory access control, which contains details, rules, and policies. For example, in here, with the Firefox process, have access to my Firefox log file, and Firefox have write permission to my file. So LSM is Linux security model, which is the Linux Mac solution. So the core of this LSM is 200 plus LSM hooks living throughout the kernel. And the LSM, different LSMs access information and maintain access control through these hooks. There are two types of hooks. A void hook is usually a void function that notifies LSMs something happened in the system. For example, file free means it has a hook, tell the security, the LSM, this file is being freed. So you probably don't need to track anything with it anymore. There are also int hooks. Int hooks can be used to notify some information to the LSM, but it also allows the LSM to deny an operation. For example, in the file open path, it will call to security file open hook. And if any of the LSM say this is not allowed, we'll return a non-zero error here, and it will deny this open operation. Okay, the different LSMs will implement their own function. This is AppArmor's version of file open hook function, and I remove all the logic here, but that's a very key point of this this LSM. And then LSM registers that to the file open hook. So when security file open is triggered, AppArmor will have a call whether this is allowed. So inside the LSM hook, this file will have this marker which expands to a logic look like this. For every LSM that have a hook, they will try to call this file. If anyone says this is not allowed, this operation is blocked. Otherwise, this is allowed. Okay, what's the PI for BPF LSM? So the design is like this. For in-kernel LSM, there are a lot of logic in the kernel, and there are policies and tools to support it in user space. But for BPF LSM, we remove all this in-kernel logic with BPF programs. Of course, we still need this hook, and everything just hook here. And then we have user space policies, tools. And sometimes you want a daemon to own all your BPF programs. Sometimes you do not want. There are other ways to have a daemon-less solution as well. So the use case is kind of straightforward. For your LSM, you need to be very flexible. Sometimes you only need one hook. Sometimes you need 200. For example, systemd have one LSM hook that is implemented in BPF. And second, programmability is very straightforward. There are so many different ways to enforce your access control. And alternative of BPF LSM is literally the in-tray LSMs, and that's easy to answer. So hook point, we do something similar to any other LSMs. We look at file open, and we register that. But this thing is a little bit of a surprise. This thing is just a function return 0. How would this work with BPF? So we use some magic that's enabled by BPF trampoline. The BPF trampoline is a small function generated at the runtime with like a JIT engine. And its primary work is to call a bunch of BPF programs. So there are a few benefits. First, it uses direct calls to the BPF program, so it's faster when you call, especially when you call multiple programs on the same hook point. Second, this provides a reliable access to function argument at function return time. This is not, if you use kprop, you sometimes have to save your arguments if you trigger a return hook and put them together. And with BPF trampoline, you don't have to do that. The BPF trampoline have a special mode called modify return, which allow a BPF program to modify the return value of the target kernel function. This has been used, I think, initially in array injection, and now we're borrowing this to the BPF LSM. So how does this work? This is the original function, and I show here in assembly there's a no op here. People sometimes call it F entry, no op. And this is BPF trampoline, and I want to use this to call this BPF program. And this program will try to modify the return value of this function. So at the runtime, this one is modified to call into the trampoline. And how does this work? So first, we call into this function, and this immediately call to the trampoline. And the trampoline will call this function, but not at the beginning, right behind this no op. So it go back here. And if there's some other logic, it will run, but in this case, it's just return 0 here. And we'll know, OK, this one returns 0. Then the BPF program will come in and try to do the logic. And it will have a modified return value. And then we'll return that to the caller. And here we need to skip a frame, because otherwise it's going to return to this function, but we want to return to its caller. So there's a little bit of detail I didn't show here. This actually didn't go to the BPF trampoline directly, but that goes through ftrace code first. But in this case, we can imagine just go over there. Now, building blocks. We have created two major building blocks. One is local storage, and we add some BPF kfuncs. So the security data usually, the LSM usually want to attach some data to each kernel object, like the inode or a task. And this is implemented as a big data block that allocated for each LSM. This could be SE Linux, maybe there's another one later. These are fixed size. And the benefit of this approach is like these data blobs have the same lifetime as the inode. If it's allocated together and freed together. However, this doesn't work for BPF, because at BPF, we do not know the size of this, all this data at the boot time. So to do that, we have a pointer and pointing to a new structure, and this structure has the capability to maintain multiple values. And this will serve different use cases of BPF because there could be multiple maps that want to attach to an inode. There's a problem with this approach because to access the final value, we have 3 pointer dereference, and that takes a lot of time. So I will skip this for the sake of the time. And BPF LSM in the community has been working very well, I would say. In systemd, we have one hook that justifies that we only need one hook. We don't need to enable others. With BPF LSM, it's used by big companies because big companies have special rules about everything. And there's open source solution, Tarragon, and there are more coming. And there's improvement being shipped. And the use case is evolving quickly. There are always new use cases coming to my desk. So let's move on to the fanotify. There's actually some limitation with LSM. The rules are sometimes local, or usually local. Say the LSM only want to protect some key files. Right? I want to protect my certificate. I don't care about a log that get read by random process. But the LSM hook is always global, meaning file open hook is always triggered on every file open, even when I only want to protect one file. So now we have a use case. Right? I have use case for my Pi. I don't even know what my solution would be. I have a use case. I want to apply security rules to a set of files, not all the files, and I want it to be efficient. And one of the details I want to add here is that often I see users want to protect a subtree in the VFS tree. And that's a good use case, and that's something I get chased by the user. How can we do that? And alternative is BPF LSM and maybe other LSMs. Next, okay, let's talk about this. fanotify is the file system notification system in the Linux kernel. This also provides access control, which is similar to LSM. It's called a permission event. It's usually used by antivirus scanners. BPF fanotify can have rules locally to a file, a directory, or a superblock, which seems a good fit for our use case. So how does the permission event work? Let's say this is a user process, this is a monitoring daemon, like antivirus scanner. So when this user wants to open a file, and it turns out this file is being monitored by the daemon, this process will sleep. And this daemon will trigger something, will read a metadata in its fanotify file descriptor. And this one contains a FD to the file being accessed. So the daemon can scan the file and see whether this is OK to do this operation. And once the daemon makes a decision, it will write a response back. In this case, it says deny. This FD will be EPERM, and that will deny this operation. And this is very attractive to me. fanotify have per inode, per superblock, and also per mount rules. In the inode, you see there's a few masks that knows what are all the events people care about this inode. And this is a pointer to details of all these events. Similar, we have something in the superblock. I want to highlight this is a filter that embedded into the inode. Recall that with BPF LSM, I have to do 3 pointer dereference to get my value. And this is right there. It's going to be much faster. So my use case looks like this. I have a user space daemon rules that combines BPF LSM and BPF fanotify program together. I use fanotify to protect the key files I care about and use LSM to do everything else. So now I have the full story of my use case. I want to apply security rules to a set of files, and specifically for a subtree in a BPFize. And what we're doing can also help antivirus scanners if they want something. Right? Imagine this permission event. We need to sleep, wake up, and go to sleep again. If we have something right here in BPF, we do not need to sleep. We make a decision, we have it's valid or it's denied. If the handler cannot make a decision, then we defer to the daemon, which is going to save us a lot of time. So we will have a handler look like this. This is ops. We have the handler, which is the key function here. And we have some init and free operations. And we have a name to refer to this. So we can have different of them in the same system. So we're going to use that with the struct ops. The struct ops starts with define an interface. Like for TCP, there's struct ops for congestion control. For SCADX, there's one for the scheduler. And we can have multiple implementation in the system. I want people think more about TCP congestion control because you have different algorithms you can use. And one of the interesting things, like for the same interface, we can implement that with the kernel module or with BPF. With the kernel module, the benefit is you can use all the exported symbols, like all these functions. You get a lot of flexibility. But if you use BPF, it's safe. Your program is verified, and you know you will not crash the system. OK, next building block. I add a BPF is a subdirectory helper that we'll see by subtree use case. And to hold this subroot, this D entry, I let a BPF program to hold a reference to the D entry. Then I can compare any file I want to open against this D entry with this kfunc. Finally, I started working with the community. There's multiple rounds of review with both VFS and BPF maintainers. OK, this is my pie for BPF fanotify. But it didn't go well until now. So the primary problem comes from subtree monitoring. Recall that we have a mask in the inode, and we have a mask in the superblock. If I want to monitor a subtree, unfortunately, I cannot use this mask. I have to use this one instead. And then BPF will decide whether it matches a subtree. As a result, it's not really local anymore. Also, this helper is not much faster, and our brilliant users have come up with ways to work in the path structure in BPF. In other words, this is not so attractive either. Next, holding a D entry in a BPF map can be risky. For example, if you want to unmount this and you're holding a D entry, that unmount may fail. We need a solution there as well. Another reason is it seems like antivirus scanners may not need an in-kernel fastpath for their fanotify use. And actually, I see people argue Linux doesn't need antivirus scanner at all. Finally, the alternative, BPF LSM, is good enough in your use case so far. So what's next? First, I will present fanotify fkernel recipes, which is done. Hopefully, I'm going to get more users, and people give me more feedback what it could be useful. Next, I think it's really important to run some benchmark and see my theory of like the embedded filter is much faster. I want a number for that. Finally, I want better solutions for subtree monitoring. And over the time, the use case may evolve. People may tell me, no, it's not useful at all. Or people will tell me, now it's time to bring it back. We need it. We'll see. Okay, thank you for your attention. Any questions?
For the BPF LSM, you mentioned a daemon that holds all the BPF programs, that loads all the BPF programs. Sorry. You have a daemon who loads all the BPF programs and just they're tied to that daemon. How do you protect against the daemon dying and then the BPF programs going away and then having things going through?
Yeah, so the question is, if you have a daemon, how do you protect it? And I think it depends on the rules you want to implement. For example, it's common to have the daemon when the daemon is killed or stopped, it fires some alarm. And hey, something weird happening here. And that's one way. And other way would be like you can ping the BPF program in the BPFize. And when even the daemon dies, those BPF programs are still working. And you can even set up other LSM rules to block anything that stops these BPF programs. Like you want to delete anything, or you want to delete this program from this BPFize, you can block that. So there are multiple ways, and at the end of the day, it depends on what you want the behavior to be. Of course, in the very last case, we block anything. To really stop it, we need to reboot the system because it's permanently enabled and there's no way to kill it.
Thanks.
It's a question about the very start of the presentation. Do you know what's actually, what sauce goes with snails? It's garlic butter. It's not pesto. Just wanted to mention. There's no basil in with snails. All right.
I'm sorry, can you repeat the question?
With snails, escargot in French, we serve garlic butter, not pesto.
Well, the one I had a while back is with pesto sauce.
Yep.
You mentioned that one of the application for I forgot the name, but Notify BPF or something like that, sorry, is antivirus scanner. Do you know if any provider for this tried to use the solution and had any results, or is it like very early stages and no one really used it in real conditions yet?
I think there are a few antivirus scanners, they use fanotify right now. And I tried to reach out to them, but hadn't got any luck yet.
Okay, thank you.
Hi, thank you for your talk. So my question is regarding the fanotify fastpath. If I understand correctly, this is only beneficial if you only want to monitor a subtree. But if the antivirus scanner wants to monitor all subtrees in the system, then you essentially have the initial situation of just having a BPF LSM on the open hook, correct?
Yes, that's correct.
So in the case of antiviruses, it would have limited usage in terms of optimization because generally they want to monitor everything rather than a particular file system. Is that correct?
I think that depends on the design of the antivirus scanner. And to be honest, I'm not expert of this, and I don't know. But I think one thing that benefits them is that if you have something in the kernel that make a decision for at least part of your request, that will make the system faster.
Okay, so it's easier to filter out subtrees that are not interesting.
Oh, if we care about every subtree, that's a different story.
Yeah.
But in like our use case with BPF LSM, we usually have different rules, and there's often many files we don't care, and we want to avoid like actual cost when we access those files.
Okay, makes sense. Thank you.
I was wondering if with BPF mode combined with the trampoline mechanism, it would be possible maybe to rewrite the arguments before they are sent to the antivirus just to fool it. I mean, you're using a lockdown PC which prevents you from doing any productive work. You just want to bypass the antivirus. Maybe it would be possible to load BPF code which just modifies the argument, says that any file is transformed to devnull, and the antivirus says, okay, devnull is fine, and then it changes the file name back and continues to the syscall. I don't know.
Yeah, I think that could be a very good idea. Thanks for the recommendation.
Okay, thanks for confirming.
I just wanted to follow up on the suggestion of trying to fool an antivirus. I believe there was a presentation some time ago which was talking about a time of check, time of use vulnerability when you're using BPF for scanning syscall arguments. So if you don't wait for the data to reach into kernel memory and just try to access it from user space, there's a possibility for a malicious user space program to change the data after the BPF program has checked it, and thus fooling the antivirus program. So if you're dealing with a lockdown system that is doing something like that, maybe you could use that to bypass the antivirus program.
I see. I'm not very familiar with the talk you mentioned. I will study what's going on with that. Thanks for the information.
So thank you.